Okay, everyone. Assalamu alaikum. I hope you guys are all doing well. Can someone please confirm if you can hear me clearly and also see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, good. So let's begin. We were doing P1 integration and we covered a couple of concepts in the last session. So basically, we've talked about how to integrate functions already using this rule, the power rule of integration. So if you have ax plus b whole raised to power n, some linear expression raised to power something, how do you integrate that? You add 1 to the power, you divide by the new power, and you divide by the derivative of the base of the power, right? So that's the rule that we discussed. We did a number of examples in this. In the last class in particular, we talked about the different applications that we have for integration, right? So one application is that if we have a derivative, how can we find the original function using that derivative? So if you have dy over dx given like this, for instance, 2x squared minus 5, how do you find the equation of the curve from that? So we use integration for this. When you do integration, you have a plus c in that integral. And then to find the value of plus c, you have this point given in the integral. You put that point, put the value of x and y, and that gives you the value of c, and you get the equation of the curve that you're looking for. That's one application of integration using the derivative of a function, finding the equation of that function, right? That's one use of integration. Then we talked about this other notation that we have where we have limits with an integral. So something like this, if you have a number written on top of the integral and a number written at the bottom here, these are called limits of the integral, right? This number is called the upper limit, and this is called the lower limit. How do you evaluate integrals like this? You basically do integration like you normally do, right? You apply the integration rules, you apply the power rule, and once you've integrated, you just input these values. You input 2 and 4, right? So 4 is the upper limit. You first input the upper limit in that integral, then you input the lower limit, and then you subtract those two cases, right? Let's get the lower limit was 2. You input these limits, subtract the case with the lower limit from the case when you have the upper limit, right? You do the subtraction and you get the result. The end result that you get from this case is a numerical value, right? After inputting those limits. Now, in this case, since you would have a plus c with the upper limit and a plus c with the lower limit, the c's are going to get cancelled. So you can actually ignore plus c in cases like this as well. You can choose not to write c as well, and it would still be acceptable. Whenever you have limits, you can ignore the value, ignore plus c as well. But otherwise, if you don't have limits, you always put plus c. Okay. Then what was the use of this in the use of this limits within use of this integration with limits? We talked about this example that if you had to integrate this, for instance, 2x minus 3 with integral with limits 2 to 4, the result that you get is the area under the graph of this line from x equals 2 to x equals 4. So basically, integration with limits is used to find areas between graphs and x-axis, area between graph and y-axis. That's one use. And as we will see later in today's class, it's also used to find volumes of revolution. We'll talk about that today. So this was the formula that we did. Area between a graph and x-axis. If we have to find this area, for instance, this is the equation y equals x squared plus 2. This is the curve that represents that equation, represents that function. If you had to find this shaded area, this yellow shaded area, which is bounded by the curve and the x-axis, and it's between x equals 1 and x equals 3, you use this formula for finding this area. Area is given by integral of y with respect to x. Limits are values of x here. Lower limit and upper limit, you just input those limits here. Now, when you use this formula, you have to be careful that y should be the subject of the function that you're given. In this case, the function given was y equals x squared plus 2, so y was already the subject. If it was not the subject, you would have to make it the subject first, okay? In this case, it is already the subject, so you don't have to do anything with that. You just input this value of the function, input the limits from 1 to 3, and you get the result. That gives you the area of the shaded region. That's the area between the graph and the x-axis, right? That's one example that we did. Then we did a number of other examples. If you had to find this area, we did integration for this. If you have area below the x-axis, the area value from the formula turns out to be negative. You just write it as a positive value at the end, and you get the result. Then we looked at this case when you have some area above the x-axis, some area below the x-axis. What do you do in this case? You have to split your working into two parts. You first of all calculate this area separately, and you calculate this area separately, and then you add them both together, right? So you first make the negative area positive, and then add them up together, right? You have to split it into two parts. That's what we talked about. And then we talked about area between a graph and y-axis. For this, we have this formula, integral of x with respect to y. So in this case, x needs to be the subject, and limits are values of y. So if we have a function like this, y equals 2x cubed plus 5, and you want to find this shaded area on the graph, this is area between the graph and y-axis here, right? So one boundary is the curve, and the other boundary is y-axis, and we're looking for area between y equals 5 and y equals 8. How do you find this area? The formula for this is this thing. Integral of x with respect to y, limits from a to b. Now you have this function, you first have to make x the subject. That's what we did in the last session. We made x the subject, then we integrated that thing with respect to y and input the limits from 5 to 8, right? And we got to the result at the end. And if you have to find area between two graphs, we discussed this. In order to find area between two graphs, you have to find area between the upper graph and x-axis, and subtract from that the area between the lower graph and x-axis. So essentially, it's the area under the upper graph minus the area under the lower graph. This is all that we discussed in our last session. All right. Now, first of all, you can let me know if you have any problems in any of these concepts, so we can discuss those problems. If you have attempted any questions on the worksheet already, you can also let me know about them. Maybe we can try one question from the worksheet quickly, and then we will also want to discuss the last concept that we have in this topic, which is volume of revolution. Okay, so we want to complete the concepts today so that you can have a couple of days to do some practice questions, and then in the next class we will have a look at some problems from the worksheet. Okay, by the way, next week expect 5 classes. So we would have classes from 2 to 3 p.m. or maybe 2:15 to 3:15 p.m. Tuesday, Wednesday, Friday, Saturday. 4 classes these, and then that Tuesday night class, we will keep that class as well for now. So in the next week, we will have 5 classes. So what I'm going to do is, in the class that we have at night on Tuesday from 10 to 11:30 or something, in that class, we will be doing practice questions on integration. And in the morning class, in the afternoon class on Tuesday, we will actually be starting functions, okay, which is our next topic. We will be starting functions in our afternoon class. And in the class that we have at night, we will be doing practice questions on integration from the worksheet. So we could actually extend that class as well. As long as you have questions, we can discuss those questions in the next class, okay, in that Tuesday night class. So next week, expect 5 classes. 2 classes on Tuesday, 1 in the afternoon, 1 at night, and then Wednesday, Friday, and Saturday from around 2 to 3 or 2:15 to 3:15 p.m. Okay? So keep that in mind for the next week. This is all that we did in the last week, in the last class. Let me know if you have any particular questions. We could perhaps have a look at one quick question, and then we start with the volume of revolution concept. Question 2, part 2. We haven't done this yet, Abdullah. This is volume of revolution. We will be discussing this concept today. This is not something that we've done for now. Anything apart from this? Any question from the worksheet related to area between a graph and x-axis or area between a graph and y-axis that you've attempted until now, that you're having problems with? Okay, what we can do is we can have a look at one of these questions. So in fact, we looked at this particular example in the last session, right, where we had to find area between these two graphs. Let's actually try this right now. This was taken from the worksheet. Let's do this particular part of this question. Or let's actually complete this question. And then we start with the concept of volume of revolution after. Because this is question number 27 from the worksheet. I took that diagram from this particular question. Let's try this quickly. By the way, just to check, is my voice clear for everyone? Is there any background noise? Actually, I have my fan on right now. I think it's making some noise. But do you hear anything in the background? Or is it okay? Okay, all right. Thank you so much. Okay, good. So let's have a look at this. Question number 27. Let's try this. It says the diagram shows parts of the curves y equals 9 minus x cubed and y equals 8 over x cubed, and their points of intersection P and Q. The x coordinates of P and Q are A and B respectively. So these points P and Q, they have these x coordinates A and B, right? These are the points of intersection of these two graphs. The x coordinates are A and B. Now, in the first part, they ask us to show that x equals A and x equals B are roots of this equation. We need to show that x equals A and x equals B are roots of this equation. Okay. And then they ask us to solve this equation and hence state the value of A and the value of B. Okay, so first of all, so there are two parts of this particular part. First of all, they ask us to show that x equals A and x equals B are roots of this particular equation. Now, if we knew the value of A and the value of B, we could input those values here in this equation and show that they satisfy this equation. But the problem is we do not know what the values of A and B are. So we can't really input those values here in this equation to show this, right? So what can we do instead? What do A and B represent? A and B are the points of intersection, are the x coordinates of the points of intersection of these two graphs, right? A and B are the x coordinates of the points of intersection of these two graphs. How do you find points of intersection? In order to find points of intersection of any two functions, we solve them simultaneously. That's what we can do. We can say, let's start the process of solving them simultaneously. We have one equation, which is y equals 9 minus x cubed. And the other equation is y equals 8 over x cubed. These are the two equations that we have. What we can do is we can start solving them simultaneously, right? How do you do that? You have y the subject in both of them. You can just equate both functions. That gives you 9 minus x cubed equals 8 over x cubed. So x equals A and x equals B, they have to be roots of this particular equation. Now they are asking us to show that this equation is basically like this. What we can do is we can just try rearranging this equation and see if we can get to that form somehow. So let's multiply by x cube on the other side to get rid of the fraction. What does that give us? 9x cubed minus x raised to the power 6 equals 8. Now take all terms to one side. If we were to take everything to the right side, that gives us x raised to the power 6 minus 9x cubed plus 8 equal to 0. And that's exactly what we had to show there. X power 6 minus 9x cubed plus 8 equals 0. That means these two values of x, A and B, they are supposed to be roots of this equation, right? Because that's the equation that we get when we solve those two functions simultaneously. Okay? So that proves this first part. We're done with this thing. So this proves that x equals a and x equals b, which were the x coordinates of the points of intersection. They are the roots of this equation. Now they ask us to solve this equation and hence find the values of a and b. How do you solve this equation now? It's x power 6. Do we know how to solve x power 6 equations? How do we solve this equation? Any idea?
The substitution.
Substitution. So
Yes,
you
sir.
can see we do not know how to solve any equations that have powers greater than 2. This is 6. We don't have a direct way of solving this. However, since the powers are in the ratio 2:1, right? You have 6:3. Remember what we did in quadratics? Whenever we have powers in this ratio 2:1, we can use substitution to convert this equation to a quadratic form, right? This is a disguised quadratic equation or a hidden quadratic equation. All we have to do is do a substitution. Whatever is the smaller power, replace that with the new variable. Let's say u equals x cubed, and that gives you u squared minus 9 times u plus 8 equals 0. And now we can solve this quadratic equation, right? How do you solve this quadratic equation? This becomes a u squared minus 8u minus u plus 8 equals 0. That gives us two factors, u into u minus 8 minus 1 into u minus 8. And we get two factors, u minus 1 and u minus 8. Which means u either equals 1 or u equals 8. Now, we were actually looking for values of x, not u. So we can put that substitution back now. We can say this means either x cubed equals 1 or x cubed equals 8. So one value of x that we get is x equals 1 and the other value of x that we have is 2 by taking cube root on both sides. Okay. Now, we were looking for values of a and b. So a is supposed to be the smaller of the two values, b is supposed to be the larger of the two values. So all we have to say is, this means a equals 1 and b equals 2. You have to write the values of a and b like this, a equals 1 and b equals 2. That's what we had to do in the first part. We have found the values of a and b. All right? No problems? Okay, let's look at the second part now. Part 2 of this question. Now in part 2, they ask us to find the area of the shaded region between the two curves. Okay, so now we know the value of a is 1 and the value of b is 2. So we have these two limits now that we can use. We need to find the shaded area. Now, how do we describe this shaded area? This is not area between a graph and x-axis or area between a graph and y-axis that we could use the formula for directly, right? This is area between two graphs. Okay. What we can do is we can say, let's find this area. So this is the upper curve. Let's find the area between the upper curve and the x-axis. So you find all of this region. Okay. You find all of this region. Now, this region also includes this region that we do not want, right? We don't want the area of this region. So when we find the area between the upper curve and the x-axis, that will give us this additional region as well. So now what we do is, we subtract from that the area between the lower graph and x-axis. So we subtract from that this area. And that is going to leave us with this shaded area in the middle. Okay. So we find the area under the upper curve and subtract from that the area under the lower curve. And that gives us the shaded region between the two graphs. That's all that you've got to do. Okay. Now let's try that. So which one are we calling the upper graph? This is the upper graph, right? Because this is in the shaded region. This is the upper part. This is the upper graph. And in the shaded region, what's the lower graph? This is the lower graph in the shaded region. That's y equals 8 over x cubed. Let's find areas for both of them. Now, let me write that down here. So we have an upper graph and we have a lower graph. And do the working separately. we can say the upper graph has this equation. It's y equals 9 minus x cubed. This is the function for the upper graph. And then the lower graph is y equals 8 over x cubed, which we can write as 8x raised to the power minus 3. This is the lower graph. Now we just need to find areas between these two graphs using the formula. Remember the formula, area between a graph and x-axis, that's given by integral of y with respect to x. Limits are from x equals a to x equals b. Let's use these limits and find this area and see what we get. For the first function and for the second function, area between graph and x-axis, that's going to be 9 minus x cubed, integral of this with respect to x, with limits from 1 to 2. Right? These are the limits that we have. From x equals 1 to x equals 2. Now let's integrate this function. First of all, what's the integral of 9? So just multiply that with x. So we have 9x minus x raised to the power 4 divided by 4. And then you input the limits from 1 to 2. Okay. Now let's input values. It becomes 9 into 2 minus 2 raised to the power 4 divided by 4. Subtract from this the case when you input x equal to 1. That's 9 into 1 minus 1 raised to the power 4 divided by 4. This step is important. You can't skip this step. You have to make sure that you write down, you input values in the limits. You have to show the step. And now you can write down the result from the first bracket and from the second bracket. 18 minus 16 over 4. That's giving me 14. Subtract from this 9 minus 1 divided by 4. That's 35 over 4. So 14 minus this, that's giving me 5.25, 21 over 4. Is that correct? 21 over 4, that's the result that I'm getting from
Yes, sir.
the first graph. Okay, now let's do the second one. Now let's apply the formula on the second graph as well. Integral of 8x raised to the power minus 3 with respect to x. Limits are again from 1 to 2. Let's integrate this function. 8 remains as it is. Add 1 to the power minus 3 plus 1. It's going to be minus 2. It's not minus 4. Be very careful when you're doing this. Minus 3 plus 1, that's minus 2. Divided by minus 2. And then you input the limits. Limits are from 1 to 2. Now, before you input limits, it's going to be easier if you simplify this first. 2 and 8 get cancelled and you're left with 4. So you can write this as minus 4 over x squared, right? This negative will remain. So that's this negative. And you have 4. X raised to the power minus 2 could be taken to the denominator. And you have minus 4 over x squared with limits 1 to 2. Now you just input the limits minus 4 over 2 squared. Subtract from this minus 4 over 1 squared. Always write these two terms inside brackets, right? Write the upper limit, the whole thing inside brackets, and the lower limit inside brackets, so that you're not making sign errors, plus minus errors, because you have this negative and this negative, it's going to become positive now, right? So what do we get from this? Minus 4 over 4, that's minus 1, plus 4 over 1, which is 4, and this results in 3. So the area under the upper graph is 21 over 4, area under the lower graph is 3. The shaded area is just going to be the difference between these two values. That's 21 over 4 minus 3, and that's going to give you 9 over 4 or 2.25. That's the area of the shaded region that we were looking for. Any problem with this? No?
No, sir.
So yeah, that's how we find area between two graphs. All right. Okay, let's have a look at the next one now. Now it says the tangents to the two curves at x equals c and so x equals c, where c is between a and b, they're parallel to each other. Find the value of c. Okay, now let's try to understand what it means by this. So there's some point x equals c, some point where the x coordinate is c, and this point is between a and b. So c is greater than a and less than b. That means it's somewhere in this region between a and b, right? So it might be somewhere between this. Let's say it's here. We don't know where exactly it's going to be. We can't assume it's the midpoint. Okay, it's somewhere between these two values. At this point, what happens is the tangents of the two curves, they are parallel to each other. So at this point, if you were to draw a tangent to one graph, let's say it looks like this, the tangent to the other graph at this point, they're saying it should be parallel as well. Now, it might look like this if it was very exact. The tangents are going to be parallel. So it's a situation like this, that when x equals c, at this point, the tangents to the two curves, they are parallel to each other. All right. We need to find the value of c. Now, how do you think about this? If the tangents to the two curves are parallel, what that means is, at this point, both the graphs, both the curves should have the same gradient, right? If the tangents are parallel, that means the gradients of the tangents are the same. If the gradients of the tangents are the same, the gradients of the curves are also the same, because tangent has the same gradient as the gradient of the curve at that point. So that's what you can say. Let me write that down. Now, you don't necessarily have to write it in your exam, but just for your notes, what they're saying is, at x equals c, the two tangents are parallel. The two tangents are parallel. This means they have the same gradient. And that implies that the gradient of the curves are also equal when x equals c. So basically, we're looking for that point at which the gradients of the two curves are equal. Now, how do you find gradients of curves, gradients of functions? Gradients are found using differentiation, right? So you know that one of these functions is y equals 9 minus x cubed, and the other function was y equals 8x raised to power minus 3. We are looking for the point where their gradients are equal. So all we have to do is find their derivatives, because that's what represents the gradient. That's what represents the gradient of a graph. What's the derivative of 9 minus x cubed? It's minus 3x squared. And what's the derivative of 8x raised to power minus 3? 8 into negative 3, that's minus 24, into x raised to power minus 4. These are the two derivatives that we have. We can simplify this and write it like this: minus 24 over x raised to power 4. Now, if the gradients are equal, the derivatives should be equal to each other. We say minus 3x squared should be equal to minus 24 over x raised to power 4. What does that give you? Minus 3x raised to power 6 equals minus 24. Minus 3 goes to the other side, and you are left with x raised to power 6 equals 8. And now you take sixth root on both sides, right? So you say sixth root, or you can say power 1 over 6. But remember, whenever you take an even root, just like taking square root, any even root, square root, fourth root, sixth root, whenever you take that, you always put plus minus. All right. So in general, you always put plus minus. So you would say x is equal to plus minus 8 raised to power 1 over 6, or sixth root of 8. And you can see what this value turns out to be. 8 raised to power 1 divided by 6. That's giving me 1.414. Do we need an exact answer, or no? Okay, so we can write this as 1.414. So we have plus minus 1.414. We're getting two values of x. These are two values of x at which the gradients are equal. However, we were looking for this point C, and we are given in the question that C is between A and B. That means C has to be a positive value, right? Otherwise, we could have a negative result as well, but the question says C is supposed to be some positive value, right? Because it's between A and B. A and B are both positive. So because of that, we only consider the positive value here, and we say C therefore should equal 1.414. To three significant figures, you could write it as 1.41. And that's your final result. You could also write it as square root of 2. Your calculator would give you exact value, I think, for this as well. If you try this, I'm not sure if it gives you or not. Let me see. 6th root of 8. Okay, calculator for some reason is not giving the exact value, but this is also square root of 2. The reason for that is 8 could be written as 2 raised to power 3 whole raised to power 1 over 6, and that gives you 2 raised to power 1 over 2, which is square root of 2. So exact value for this would be square root of 2. If you were asked for exact value, you could write square root of 2. Otherwise, in this question, since I don't specify anything, this is also acceptable. You can write 1.414. Any problems with this? Any questions, anyone?
No, sir.
No problems? Okay, let's start with our next concept then. And that is volume of revolution. Let's have a look at this. Volume of revolution of two graphs. Of not two graphs, volume of revolution between a graph, volume of revolution for area between a graph and x-axis and area between a graph and y-axis. That's what we want to do. But before we do that, let's try to understand what volume of revolution means in the first place. Let's try to understand this first. Let's say we have a graph like this. We have a line, for instance, y equals half x, right? This is the line that we have, y equals half x. And we want to find this volume that I'm just going to show you. Y equals half x, what is this line going to look like? It's going to be a line that passes through the origin and goes like this, right? Assuming the gradient is 1 over 2, this is what the line might look like. Okay. Now let's say this point is 0, and maybe there's another point here. This point, let's say this point is, I don't know, x equals 6 maybe. The area between the graph and x-axis in this region, what is that going to be? This region is a triangle like this, right? This is the area between the graph and x-axis. Now, what we want to do is, we want to rotate this area about the x-axis. So think about this. Think of this line. Think of this line as the axis of revolution, as the axis of rotation. Think of this line, the x-axis, as the axis of rotation. If you were to rotate this area about this axis, can you try to visualize that? You're rotating in 360 degrees, 360 degrees about the x-axis. What is the shape that you're going to get? Rotate this area about the x-axis, you would get a shape that looks something like this. When you rotate it, this line is going to rotate 360 degrees about the axis, and you would end up getting a cone like this. Does that make sense? if this is the axis of rotation, x-axis, you are basically rotating this shaded region about the x-axis. This is the shape that you get. It's a cone that looks like this. Can everyone try to visualize that? Does this make sense to everyone? Yes?
Yes, sir.
We want to find the volume of this figure, right? We want to find the volume of this figure. Now, this is a cone. We know how to find volume of a cone. We have a formula for that. What's the formula for volume of a cone? Volume of a cone is given by V equals 1/3 into pi r square h, right? We know how to find this volume. How do you do this? Do we know the radius? If x is equal to 6 here, what about the value of y? We can input x equals 6. That gives us y equal to 3 corresponding to x equals 6. That means at this particular point, the y value is 3. Okay. So what's the radius of this cone then? This is the radius of the cone. That's 3. What about the height of the cone? Height is this height, right? From that vertex to the base of the cone, that is 6 units. We could find the volume of the cone like this. The volume would be given by 1/3 into pi into r squared, which is 3 squared, into h, which is 6. What do you get from this? It's going to be 18 times pi, right? That's the volume of cone. Volume of this cone that we drew here. All right. Now, this is called volume of revolution. Now, this same volume could actually be calculated using integration as well. And as with area, the use of this integration would be that what if we had a curve instead of straight lines? That would not be a standard figure, and you would not have a direct formula, the standard formula for that volume. For that, integration is going to be helpful. Now, let me first show you how you could get the same volume using integration as well. So basically, this is the formula that we will be using for volume of revolution about x-axis. It's integral of y squared with respect to x multiplied by pi, and you have some limits here, x equals a to x equals b. That is the formula that we will be using for volume of revolution about x-axis. Now, let me first show you how you could get the same volume using this formula for this particular shape as well. Let's try that. What's the function? Function was y equals half x, right? Let's input values in this formula. So y equals half x, that's the function. Now, for using this formula, you need y squared. What would y squared be? Y squared would be 1/4 into x squared, right? Just square this whole thing. That gives you 1/4 times x squared. Now you apply this formula, input values in this formula, and see what that gives you. Vx equals pi into integral of y squared, which is 1/4 times x squared. And limits are going to be 0 to 6. You're rotating about x-axis, right? So the limits are going to be values of x, 0 to 6. Let's input those limits here, 0 to 6, and see what that gives you. Pi into integral of this thing. What's the integration of this? 1/4 times x squared. 1/4 remains as it is. Integral of x squared is x cubed divided by 3. Right? Limits are from 0 to 6. Now, you could simplify it like this. This constant could be written outside, 1/12. So you have 1/12 times pi into x cubed. Limits are from 0 to 6. You just input these limits now, 1/12 pi or pi/12, multiplied by 6 cube minus 0 cube. See what that gives you. 6 cube is 216 divided by 12, that is 18. So you get 18 pi from this as well. And that's the same thing that you got from the volume of cone formula above. Now, using integration for this might be an overkill, as in you have a formula for this directly. You could find that area, find that volume using the volume of cone formula as well. However, this basically shows you that if you know the function for that graph, the function is y equals half x, right? Y equals half x. Now, instead of a straight line, you could have some other function as well. You could have a curve as well. You could basically use this formula to find that volume of revolution for figures for which you do not have any standard formula. Okay. Now, let me write that down. So instead of this figure now, what if you had something slightly different? So what if you had a shape like this instead? Let me draw another diagram here. Let's say you had a shape that looked something like this. This is the y-axis, this is the x-axis. Let's say you had this shape. Okay, I'm sorry, let's try again. Okay, so you have a shape like this. Now this is the graph of y equals x squared, for instance. Now, okay, this is a curve. Now this is just the right side of the graph. The left side would look like this. Right, but we are not interested in the left side right now. We're just looking at the right side. Now let's say there was some point here which was maybe x equals 1. When x equals 1 here, what's the corresponding value of y? That's also 1 on this graph, y equals x squared. And let's say there was some point where x was equal to 2. Let's say this is x equals 2. And at this point, 2 squared, that's 4. This value is 4. And now let's say we have this shaded region. Area between the graph and x-axis. If you wanted to rotate this area about the x-axis 360 degrees, again considering x-axis as the axis of rotation, so you're rotating this about x-axis, what figure would you get from that? You would get a shape that looks something like this. It will be a shape like this, right? It's kind of a loudspeaker or something, right? It's a shape similar to that. This is the shape that you have. Now, you don't really have any direct formula for finding this volume, right? It's not a standard shape. It does not have straight lines. It's a curve. And we can't really find the volume of this figure using any standard formulas. Now, this is where integration comes in. How would you find volume of revolution of this figure? Let's try that. Let me write that here first. Volume of revolution about x-axis. Now this means when a figure is rotated 360 degrees about x-axis. Now let me write that down here. So what are the questions normally going to refer to? They will be saying the figure is rotated 360 degrees about x-axis, right? So this is the volume obtained when the region between a graph and x-axis is rotated 360 degrees about x-axis, right? This is the volume that we want to obtain here, okay? That we want to find here. It's the volume obtained when the region between a graph and x-axis is rotated 360 degrees about the x-axis. So this is the shaded area between the graph and x-axis. If we were to rotate it 360 degrees about the x-axis, what would be the volume obtained for that? This is the formula that we have. Vx equals pi into integral of y squared with respect to x. And you have some limits here from x equals a to x equals b. This is the formula that we will be using. This is the volume of revolution about x-axis. Now, in this case, just like we had for area, when we were finding area between a graph and x-axis, we needed y to be the subject. Now, in case of volume, in this case, we would need y square to be the subject of the function. So y square needs to be the subject. And then limits are supposed to be values of x. Since the rotation is about x-axis, the limits are supposed to be values of x. Okay. Now let's apply this formula on this figure and find the volume of revolution in this case, and see what that turns out to be. What was the function? The function was y equals x squared, right? That's what the function is. Now the formula requires y squared. So if y equals x squared, what about y squared? Y squared would be x raised to power 4. That's what you input in the formula. You say Vx equals integral of pi into integral of. So it's very common to forget pi here. I tend to do that quite often. So make sure that you remember to put pi outside the integral. Pi into integral of y squared, which is x raised to power 4 with respect to x. Limits are from 1 to 2, right? Limits are supposed to be values of x because the rotation is about x-axis. Limits are values of x, 1 to 2. These are the limits. You just need to evaluate this, and that will give you that volume. We have pi into integral of x raised to power 4, which is x raised to power 5 divided by 5. Input the limit from 1 to 2, and that gives you pi multiplied by 2 raised to power 5 over 5 minus 1 raised to power 5 over 5. And that will give you the volume of revolution that we're looking for. 32 minus 1, that's 31. So that's going to be 31 over 5 times pi. That's the volume of revolution when this shaded region is rotated 360 degrees about the x-axis. Does this make sense? Any problem with this?
No, sir.
No? So that's how you find area between a graph and x-axis. Sorry, volume of revolution about x-axis. Okay. So pi into y squared, integral of that with respect to x, and limits from x equals a to x equals b. Again, this formula is not given in the formula sheet. You will need to memorize this. Okay, these formulas are not given in the formula sheet.
Sir,
Yes.
sir, do we need to write this formula on the paper while solving the question? Does it have any marks?
No, you can directly start solving it. Although I recommend that you do write the formula first, because that saves you from careless errors in most cases. So write the formula first and then input values in that formula. I think that's going to be safer in terms of not doing careless errors, right?
Okay, sir.
Okay. Now, let's do the same thing for volume of revolution about y-axis now. So now instead of rotating some area about x-axis, let's say we want to rotate some area about the y-axis. Okay, so now we need to find the area, volume of revolution about y-axis. Let's do that now. Okay, let's think about this. Volume of revolution about the y-axis. Okay, so the same idea would apply with the y-axis as well. So now if we want to rotate something about y-axis, let's think about what happens that in that case. So now we want volume obtained when the region between a graph and y-axis is rotated 360 degrees about y-axis. Now, what does that mean? Let's consider those same 2 points again. You have point 1 here and point 2 here, x equals 1 and x equals 2. Now, corresponding to 1 on the y-axis, you've got 1, and on the corresponding to x equals 2 on the y-axis, you've got 4. And now, what you want is, you look at the area between the graph and y-axis between these 2 points. Okay. You look at the area between graph and y-axis between these 2 points, like this, and this. This is the region that you have between the graph and y-axis. From 1 to 4. Okay. We want to rotate this area about the y-axis. So now the axis of rotation in this case is going to be this y-axis. This is the axis of rotation. This is the line about which you want to rotate this area, right? 360 degrees about this axis. What would that give you? That will give you a shape that looks something like this. Right? It would look like this. It's a ball like this, right? This diagram. So this figure, basically, all of this. All right. This is the figure for which you want to find the volume. Make sense? So when this shaded area is rotated about the y-axis, you get a figure like this. You want to find the volume of this figure now. Now, how do you find this volume? For this, you have a similar formula, just like we had a formula for volume of revolution about x-axis. We have a formula for volume of revolution about the y-axis now, and that looks like this. It's pi into integral of x squared with respect to y, and you have limits from y equals a to y equals b. So now when you want to find volume of revolution about y-axis, the subject has to be x squared. So you need to make x squared the subject first. And limits are supposed to be values of y. That's what the volume of revolution formula looks like for the y-axis. Okay. Now, how do you find this volume then? In this case, you knew that y equals x squared. Now, let me write that down here. The function is y equals x squared. Now, what do you want to do? You want x squared the subject. Now, in this case, that's not very complicated because it just becomes x squared equals y, right? If it was something else, for instance, if it was y equals x plus 1 whole raised to the power, I don't know, let's say it was 1 over 2. Or maybe let's make it 1 over 3. Let's say we had something like this. Y equals x plus 1 whole raised to the power 1 over 3. We had a function like this. We would have to make x squared the subject first of all. How would you do that? You would take cube on both sides. That will leave you with y cube equals x plus 1. And then it will become x equals y cube minus 1. And then you would say x squared equals y cube minus 1 whole squared. This is what you would need to integrate in that case. Okay. So you have to make x squared the subject. Now, while we are at it, Does anyone remember how do we integrate this function? So if we had to integrate this thing, y cubed minus 1 whole squared with respect to y, how would this integration work? How do we integrate this?
Sir,
We have to,
sir, first we would increase the power by 1 of the whole bracket to 3 and divide it, and then
Y cubed minus
differentiate
1 raised to power 3 divided by 3
3,
and
differentiate what is inside the bracket.
which is 3y squared, right?
Yes.
Does that
we
work?
have to do we have to do them separately because it's not linear.
The part inside the power is not linear. We cannot use power rule here. That is not going to work, right? The power rule has condition in integration. The part inside the bracket, it has to be linear. If it's not linear, we can't do this. We can't apply power rule here. So this doesn't work. So what do we do instead? We would first need to expand it. You would need to expand it like this. You would say this is y raised to power. So a minus b whole squared, right? A squared minus 2ab, that's 2y cubed, plus b squared, that's 1. Now you would integrate each of these terms separately. So the integral of y raised to power 6 would be y power 7, and then 2y raised to power 4 over 4 plus y. That would be the integration of this. And then you would input some limits in that. Okay. So if you had a relatively more complicated function like this is what you would have to do in that case. Okay. I hope that makes sense. Now let's get back to this one. So what were we supposed to do here? We had y equals x squared as the function. We made x squared the subject first of all, x squared equals y. Now you just input this value in that formula. What does the volume turn out to be? So it's the volume of revolution about y-axis. We can represent it using Vy. What's Vy? Vy equals pi into integral of y, right? X squared is just y. Y with respect to y. Limits are from, what are the limits? Limits are supposed to be values of y. So that's 1 to 4, right? Limits are from 1 to 4. Now we integrate this pi into y square over 2. Input limits from 1 to 4. You get pi into 4 squared over 2 minus 1 squared over 2. And that gives you 16 minus 1, that's 15, 15 pi over 2. That's the volume of revolution that you get for this figure. That's the volume of rotation. Okay? And that's what we were looking for here. We found that value. So this is also something that can happen, volume of revolution about y-axis. This is how we calculate this. Okay? I hope that makes sense. Now, one final thing. Sometimes they ask you to find the volume of revolution of the area between two graphs. Now, let me show you a problem like this. Yeah, for instance, this one. Question number 39. Let me have to show you using another one first. And this is about the y-axis. Okay, let's actually just take this example. For x-axis, let's do it for y-axis. So if you had something like this now, if you had this diagram, and you wanted to find the volume of revolution when this shaded region is rotated 360 degrees about x-axis. How do you do that? Volume of revolution when shaded area is rotated 360 degrees about x-axis. All you have to do is find the volume of revolution of the upper graph, just like you used to do for the area. You would find the volume of revolution of the upper graph, subtract from that the volume of revolution of the lower graph. And that's it. That's all that you've got to do, right? You would do the same thing for y-axis as well. For y-axis as well, you would find the volume of revolution of one of the two graphs and subtract the other from that. Sometimes you might be confused which one is going to be subtracted from which one. As long as your working is correct, the volume result at the end is always going to be positive. The area result could sometimes be negative, right? But volume is always positive because you're using x squared and y squared here. So the volume result at the end is always going to be positive. Now, because of that, whatever is the larger volume that you get, you subtract from that the smaller volume. So you find volume of revolution of both graphs separately, subtract the smaller from the larger. And that will give you the volume of revolution when the shaded region is rotated, when the area between two graphs is rotated about x-axis or about y-axis. You'll find the volume of revolution for each of them separately and then subtract the results that you get. Okay? I hope that makes sense. Now, in the next class, we will be doing practice questions on this. Next means Tuesday night. Tuesday night, we will be doing practice questions on this. There's a small concept that we still need to do, which is when sometimes you have infinity as one of the limits, right? Something like this. We will see how to handle that case in that Tuesday night class as well, along with doing practice questions on integration. All right, so Tuesday afternoon at 2 or 2:15 p.m., we start functions. And then Tuesday night, we will be doing practice on integration. All right, is that clear to everyone? Any problems? No? Okay, that's it for today then. I'll see you. Yes, Azim, you're saying something?
No, I was gonna say no problem, sir.
Okay, good. All right, so I'll see you again on Tuesday then, Tuesday afternoon for functions, and then Tuesday night we start integration, inshallah. All right, that's it for today. I'll see you again in the next class. Allah Hafiz.